Hello there. Welcome to the session 6 of Unit 2. And in this section, we'll be looking at kinetic theory of gases. Let's look at the objectives of this section. 1. To state the assumption made in developing a kinetic theory of gases. 2. Derive the root mean square speed of gas molecules. 3. State the relationship between the root mean square of an ideal and its temperature. And lastly, to calculate the average kinetic energy of mono and diatomic gases. So, let us consider a fixed mass of gas contained in a cube of side L. We shall assume that the walls of the container are perfectly elastic. Let the side of the cube coincide with the axis of the rectangular coordinates x, y, z. Suppose any one of the molecule of mass m has a velocity such that it can be resolved around the 3 dimensions. Now, let's look here. The relationship between force and momentum is this, where we have force to be equal to momentum divided by change in time. And the same thing here, with the same thing here, we can represent the momentum as m times the velocity. But because it's before and after collision, we are going to multiply it by 2, so that our f here, f dot t, can be equal to 2 times mass times the velocity. In case we want to find the time for a round trip, it's going to be 2L over velocity. We know already that v is equal to what? Distance over time. When we make the time the subject, we are going to get distance over velocity. And here, our distance here right now is what? Is t. And because we are finding for a round trip, right now the distance is going to be multiplied by 2. Now, let's come and put the change in t here in this first relation, so that in making the f the subject, we are going to get 2mvx all divided by change in t. But this time around, the change in t is the whole of 2L over vx. And that is what we have here. Dividing this one by 2, dividing 2L over Vx by 2m Vx, we are supposed to get mv squared over L. But let's look at something here. For n molecules, meaning we are supposed to get v1x squared plus v2x squared plus v3x squared. That goes on to nx, vnx squared. We can present the whole of this one in the square bracket here to be as our average velocity here, so that we can put this relation in here to represent what we have here. If we do it in that case, we are going to get the n number of molecules. The n number of molecules this time around to be equal to mn vs squared. That's the average over big L. Nothing changes here. It's just this formula here that we have transitioned it to get this, what we have here. And this time around is because of the number of molecules that we have in the container that changes it. So now for n number of molecules, the average force right now becomes m times the number of molecules times the average velocity squared all over the L. And L here is the distance of the side of the box. And assuming random speed at all directions, that's x, y, and z, right now the average velocity will be equal to v squared will be equal to v squared x, v squared y plus v squared y plus v squared z, which is going to give us what? 3v squared x. Now let's relate the average force to pressure. We know from our old physics that pressure is equal to force over area. Now considering that we know that the average force right now is the whole of the deduction that we did in the previous slides. We can come and put in here our deduction that we've done for the previous slide so that we get our m times the number of molecules times the square of the average velocity, all divided by 3LE. The 3 comes in because right now we are considering, we are doing an assumption at random speed in all directions. If we do it this way, because our L here and there's an area here, both of them can multiply for us to get what? A volume. That's a big V. Also, we can just make m here and v squared here to step aside like this, so that we have the number of molecules divided by 3v multiply mv squared, the average of mv squared. Finally, in trying to bring in kinetic energy, we can bring out 1/2 mv squared here. Don't confuse yourself with what we have here. It's the same because we can just cancel the 2 here. Let me use a mouse pointer, a laser pointer. We can just cancel the 2 here and the 2 here, and this whole equation here will become the same as what we have here. But because we want to bring in kinetic energy, that's why we are doing it this way. We know that the kinetic energy is equal to 1/2 mv squared. So this whole equation can be equated to what? Ke. That's our kinetic energy. And kinetic energy here can therefore be made the subject with respect to what? Pressure, number of molecules, the volume, and that will be all. So that at the end, we are going to get 3p then all divided by what? 2n.